Gibbs free energy formula and what it means. Now that we've taken a look at both enthalpy and entropy, maybe you can understand that both play a role in terms of calculating free energy. Enthalpy is the major component, and that is in the order of kilojoules per mole. But if things are getting more random, that might help make some reactions spontaneous, and the hotter it gets, the more it'll help. But do notice that these are in the units of joules per mole. They can be as much as 1,000 times lower. So let's think of each one and each situation in terms of spontaneity, reaction direction, and equilibrium. Well, if it's negative, I oftentimes think of that as what you're looking for. That'll be a spontaneous process. As you may have seen in an earlier screencast, it's kind of a big letdown because it ignores activation energy. It doesn't mean that things will suddenly just spontaneously react, which is exactly what you'd expect from that term, but it does mean that there will be an overall lowering in the free energy for that reaction. And oftentimes that activation energy isn't as nasty as you might imagine. It could just be a little spark, right? Give it a little spark, and then it's spontaneous. I know, it doesn't really make it spontaneous, but that's how they do it. So if it's negative, the system is spontaneous, and in terms of equilibrium, you are not at equilibrium. Now, see how they say the forward direction? I had to change these slides because they kept bouncing around in terms of directions, but as you might predict, anything that is spontaneous in the forward direction will be non-spontaneous in the reverse. So hopefully that's obvious. And if it's greater than 0, it's non-spontaneous and not at equilibrium in the forward direction. And if it's at 0, well, that's a special case where you're exactly at equilibrium. And that's where this will make a nice link between everything you've learned about equilibrium and everything you've learned about free energy. This is the Gibbs free energy formula.